I recently got to teach physics of music for the first time, and what an absolutely fun class to get to teach as a physicist with a music background. I don't talk about it too much on the channel, but I was a music major in high school at a local arts magnet school that focused on different arts areas, and I was a music major. I played trumpet. I took music theory. I took music history. I learned all kinds of stuff in rehearsal about tuba speaking slowly and the pyramid of sound. And music theory teacher tried to convince me of the difference between a G sharp and an A flat, and it never quite stuck. But I loved my experience as a music major, and I'm always happy to get to draw on that knowledge whenever I can. And so when the opportunity came up to teach a physics of music class, I took it right away. And of course, as with all my classes, I wanted to know how could I incorporate some computation into a physics of music class. And it turns out there's a lot you can do with it. So every single activity we did in this class involved computation in some way. At some point, I would like to put some longer form tutorials about those activities on this channel. But for right now, I want to share with you a cool little activity I created that helps you hear the number pi. So this activity and many of the activities in this class involve the ThinkDSP library. This is freely available on GitHub, and it allows you to do sound analysis. So if you record something, you can bring it into the computer and do a frequency breakdown of it. Or it can be used to generate sound. You provide the numbers and it creates a sound file for you. So the first thing you need to do, if you want to open this Jupyter notebook for free in the description below, you can save your own copy to the drive and then you're able to edit and access that. You just click on this first play button to clone the ThinkDSP library. It'll take a minute, so go get yourself a cup of tea while it's cloning. It should give you a whole bunch of done messages. Hopefully no error messages occur. If they do, just clear the runtime, run it again, it should be fine. So this library works by first generating signals and then turning those into waves. So let's talk about what the difference is there. The first thing we're going to do as an example, we're not going to get to pi yet, but the first thing we're going to do is create an A major chord. So what notes do I need for this? I need a tonic. I need a third, a fifth, and an octave. I don't know why I wrote them in that order. It just seemed like the easy thing to do at the time. So the way a chord is structured, or the way a scale or notes are structured, is that within an octave, they've got a fixed ratio for each type of interval. So when you go from an A to the third, that's a C sharp. I'm fingering my trumpet to help me remember what the notes are. When you go from an A to a C sharp, you are going up by a certain ratio. You're not going up by a fixed amount of frequency, you're going up by a fixed ratio. And so from the tonic to the third, that is always a ratio of 5/4. So you notice we're starting out with an A of 440, we multiply by 5/4 to get the third. So that means if we started an octave up, if we started at 880, the third would be 880 times 5/4. It doesn't go up by a fixed interval, it goes up by a fixed ratio, which is different for us as physicists, right? We're accustomed to thinking of adding things. This is always multiplicative. It's always a ratio. Similarly, for the fifth, the ratio is always the tonic times 3/2, and then an octave is always the tonic times 2. What you can also specify for these signals is the amplitude. I've just decided to make the tonic the loudest. Again, the pyramid of sound, we want the loudest at the bottom, but then I've gone ahead and made the rest a 0.3 just so that we can hear them all equally. You can fine tune that if you want. It doesn't really change the physics of what's going on here. So to create an A chord, I need to add those signals together. So these names, tonic, octave, fifth, and third, they are the notes in the scale. They are individual sine signals. So this is taking those sine waves and adding them together to get a superimposed wave. Then what we need to do is create a wave from that, an actual sound wave that ThinkDSP can process. And so this, we use the make wave command. We give it a duration, a time to start at, and how much frame rate to give it. So the higher the frame rate, the higher the quality, but the more data it's going to take up. It's always nice to plot the wave. And so it does come in with a built-in tie-in to PyPlot here. So if you include a call to import Matplotlib, you can get a pi plot command here. So we're going to have this segment defined here. We're going to do the segment.plot and then have it show. And that's going to create a wave pattern like this. So this is those 4 waves added together. This is the way we in physics usually think of a wave. But we also want to be able to show the spectrum. So by spectrum, we mean how much of each frequency is there in the wave. So in this case, instead of making a wave, we're going to make spectrum. And when you do that, you get out this spectrograph here that's got our 4 frequencies. So 440, the tonic here, the third, the fifth, and then the octave. And it shows me how much of each wave is being represented. So remember, the tonic had the highest amplitude. The other 3 had equal amplitudes. The units over here are very arbitrary. I don't know if, I haven't looked into whether they actually have any significance. But the important thing is the ratio, right? That this is a ratio of 5 to 3 going from here to here. So that's really useful. Having both those representations useful because this is physically what the wave looks like. The second graph is mathematically what's going into the wave to create the top version. And now for the thing we came from, actually hearing it. So the last command in this code cell is where you can play the wave. So you ask it to wave.play. It has a built-in player that it can call on. It calls on IPython here, and that will allow you to create this little player at the bottom, and we can go hear the A major chord. Isn't it nice? You notice it lasts for 3 seconds because up here we gave it a duration of 3 seconds for the wave. And so that's handy. You can make that a longer duration if you want. And then you can use that to start to compose pieces because maybe you want some notes to be 1 second long, some notes to be 2 seconds long, some notes to be half a second long. Really cool stuff. So yeah, you get to create a chord from that. And mathematically, all you're doing is adding those signals together. You're stacking those waves on top of each other and knows how to do the superposition. So the thing I wanted to try to do was see what it was like to hear a ratio of 1 to pi, right? Every interval has a given ratio, right? 3/2, 5/4. They get really convoluted when you start to get into like half steps or an augmented fifth or something like that. But what you have here is A with A times pi. So I said, okay, let's try this. So we're going to take the tonic, and that's going to be 440. We'll start with an A again. And then let's put on top of that the pith, I guess it would be. We're going to take 440 and multiply by pi. So we're going to create an A pi chord by adding the tonic and the pith. This is now the exact same process we did before. We're just creating a pi chord instead of a major chord. You can already tell the graph looks pretty interesting, right? That's very different than what we saw before. Here's what the ratios look like. Now, what I notice here, already from the visual, those are really far apart from each other. Let's click play and see what this sounds like. So I knew that would sound weird, right? Because pi is an irrational number, nay, a transcendental number. I know that's going to be a weird ratio to me. But I'm actually having a hard time hearing the interval itself. And after listening to that a couple times and finally going and looking at the numbers on the spectrograph, I realized this is more than an octave apart, right? Because an octave, when you go from an A to the next A, an octave above that, you're doubling the frequency. This is multiplying the frequency by 3.14, etc., etc. So it's tripling the frequency, going an octave, and I guess that's not necessarily an octave and a half, but an octave plus. And it's actually really hard for our ears to hear that. I mean, let's listen again. I'm having a hard time actually telling what this is supposed to sound like. And that's when I realized I don't want a ratio of 1 to pi. I want a ratio that captures the 0.14159, etc., etc. on the pi part. I don't really want the 3. And so what I decided to do instead was make a smaller interval that still retains that 0.14159, etc. So instead we're going to take A with A times pi minus 2. right? Because subtracting off the 3, it's going to make it 0.14159, and that's going to have the opposite problem. That's going to put the pith way lower than the A, and we're going to have too broad of an interval again. But if I subtract off 2, and I have a 1.14159, right? Remember, this is about ratios. So a ratio of 1 is the same note. So it's like I'm taking the same note, it's like I'm taking A, and raising that by a fraction of 0.14159, etc. Because that's the piece I'm interested in. I'm interested in that irrational transcendental difference. I don't really want to hear A times 3. I want to hear A times the 0.14159. That's where the dissonance is really going to occur. So here we've got the exact same setup as the previous code cell, but we've got 440, we've got our A times pi minus 2, right? So I'm subtracting off the extra octave in there, leaving it with a 1. So 1 is the same note, and I'm leaving in the 0.14159, so I'm getting just that little bit of ratio there. So let's create an A pi chord here. Now this looks a little more reasonable, right? This looks like, okay, I can see how those two are produced from, now this wave is produced from 2 very similar waves. And I come down here and I've got a very close frequency distribution, right? We're going from 440 up to just north of 500. All right, now for the result. What does pi sound like? Pretty dissonant, right? Let's try that again. That's pretty dissonant. It's not quite the same as a half step, though, right? A half step is pretty dissonant. And I don't think I've ever heard that interval before in notes. And so that got me thinking, okay, I would like to compare that with other dissonant intervals. So the 2 most dissonant intervals I can think of is a half step, that's the 2 closest notes on a piano, and a tritone. So a half step, it turns out, if you, actually, let's do the tritone first, sorry. So there's a tritone and there's a half step. Half step is 2 notes next to each other. The tritone has this historical significance because the tritone was actually outlawed by the medieval church because it sounded so dissonant. It gave the priests the willies, and they decided it must be associated with the devil. And so the tritone has another name, the devil's tone. And so the tritone was outlawed in sacred music in the Middle Ages. And that kind of bled forward into the Renaissance and even into the Romantic period, where the tritone was kind of reserved when you really wanted dissonance. By the time you get to the age of jazz, they really wanted things to sound different from classical, and so they were putting the tritone in all the time, which is why when you have your jazz chords, you end up with more tritones in there. You end up with more diminished seventh and tritones and things because they wanted it to sound different. So that's one of the ways you get music to sound different over the generations. All right, so this example creates an A with a D sharp. So a D sharp is the tritone above A. Also historical significance, tritone is the opening interval on the whistle of the X-Files theme song. That's why it sounds so creepy. It opens with the most dissonant interval we know of. So let's see, we're going to create the notes. We're going to create a 440 and then a tritone above that. So that's an A to a D sharp. And you look at that wave. I mean, that wave screams dissonance, right? There's a lot going on in the interference pattern there, right? You come here, this is what the tritone looks like in terms of the separation. Let's hear the tritone. Right? Creepiest tone we know. So the pith interval sounds dissonant. And then you got the tritone. So it's actually kind of close. Bum, 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 bum. Actually pretty close there. Let's compare that with the half step, an A with an A sharp. Again, this is the 2 closest notes on the piano. And you get a very cool interference pattern here, right? You got 2 waves of very similar frequency, slightly different. That's kind of what we think of when we think of a dissonant wave. Again, compare that with the pith. Kind of a similar structure there. And that got me wondering, okay, what are the ratios for these things? Because when you're playing this in band, you're told that an octave is double the frequency. You might learn a couple of the other ratios, but you didn't really think about that. And so I started thinking about, okay, what are these other ratios going to be? And so I just did a little math there at the end, and I said, okay, a half step is going to be 466 to 440. I end up with a 1.059. Okay, yeah, they should be very close. That ratio should be close to 1. The pi over 3, it turns out, is 1.047. So actually really close to a half step, right? So the half step goes up by a ratio of 0.06. This one goes up by a ratio of 0.05. If you take the ratio of the ratios, they're only off by 1/3, right? So it's kind of cool, right? So then I said, okay, what is the ratio for the tritone? I put this one over this one, I put this frequency over this frequency, and I got out a very familiar looking number, 1.1414213, etc., etc. And I looked at that and I said, I know that number. I work with that number every day. That's the square root of 2. And to confirm, I printed square root of 2. Yep, 1.414213, etc., etc. When you do a class in trigonometry or vectors, this comes up all the time because it's the sine and cosine of 45 degrees. And it's 1 over that because that's 0.707. It's 1 over root 2, etc., etc. It's half of that, whatever. We know this number in the sciences. This is square root of 2. It turns out I didn't know this. This is the big thing I learned. Besides what pi sounds like, as a bonus, I learned that the tritone has a ratio of the square root of 2, and I didn't know that before. So there you have it. We have learned what a ratio of pi sounds like, or at least the closest ratio we can get to pi without it being more than an octave above. We also got a bonus. We learned that the tritone, the most dissonant interval we have in music, also happens to have a ratio of the square root of 2, a famous irrational number. So again, the link to this code is available for free in the description below. Feel free to try out other ratios. Hope you enjoy that, and we'll see you next time. Bye-bye. I'm not going to start with the word so. So I recently... I wanted to not start with the word so. Oh, man.